Now let's see a problem supporting the factor form of a polynomial. Say for example, I have an example problem which says form a monic polynomial of degree 3 whose roots are given to be this. Now we take into consideration all the properties of polynomials which we have discussed to do this following problem. Now in this case, as I read here, I understand that I have to form a monic polynomial of degree 3. So this makes me understand that the polynomial degree is 3. That implies n is equal to 3. Therefore, it has 3 roots. And all the 3 roots are given here as 2, 3 and 6. So we need not find any other 4th root because the only roots, the most number of roots this can have is 3, which are already given here. Now let the monic polynomial be some p of x. So I take the monic polynomial as p of x, and since this is a monic polynomial, I have the leading coefficient, which I denote generally with a naught, is 1. My leading coefficient plays a vital role in representing the polynomial in a factor form. So therefore, because it's a monic polynomial, I identify its leading coefficient to be 1. And the roots of p of x are given to be 2, 3 and 6 are the roots, where this one is represented with alpha 1 and this with alpha 2 and this with alpha 3 as we have taken in the formula. Therefore, I can represent the polynomial in the factor form as p of x equals a naught into x minus alpha 1, x minus alpha 2 into x minus alpha 3, which we have already taken in the previous case. Here, degree n being equal to 3, I stop the factors at alpha 3. Now each of alpha 1, alpha 2, alpha 3 are known, and my a naught is also known. I simply substitute in p of x. Therefore, substituting each of the values, I get my p of x is equal to a naught, which is 1, times x minus alpha 1, which is x minus 2, and x minus alpha 2, which is x minus 3, and x minus alpha 3, which is x minus 6, is what I get. Therefore, my polynomial here is in the form of x minus 2, x minus 3 and x minus 6, which on simplification gives me the polynomial. So let's simplify this in the form x minus 2 times x squared minus 3x minus 6x minus 9x plus 18. So initially I simplified these two factors and then simplify the rest, so that this comes as x cubed minus 9x squared plus 18x minus 2x squared plus 18x minus 18 2's 36. So this gives me x cubed minus 9x squared minus 2x squared is 11x squared plus 36x minus 36, which is nothing but the required polynomial. That's how I extract the monic polynomial of degree 3 with the roots 2, 3, 6 using the concept of factor representation, and thus the monic polynomial obtained is how the problem is done. Now, this is one of the most important session which connects the roots and coefficients. The roots which you're going to find for a given polynomial and the coefficients which exist in the polynomial are very much associated, and this is very useful to understand the relation between roots and coefficients, or finding the roots using the coefficients, or finding the coefficients using the roots, is how we transform from the roots to the coefficients or coefficients to the roots. So let's see how the roots and coefficients are related through the mathematical relation. So to start with, I considered initially an nth degree polynomial equation, say x power n plus p1 x power n minus 1 plus p2 x power n minus 2, so on and so forth, till pn minus 1x plus pn equal to 0. So this is the nth degree polynomial equation which I have considered, of course, which is a monic polynomial, and using this I want to connect the coefficients which are p1, p2, pn minus 1 and pn with the roots of the given quadratic equation. So let me say, for this being of nth degree obviously has n roots which need not be distinct. So I take the n roots, let alpha 1, alpha 2, alpha 3, so on and so forth till alpha n minus 1 and alpha n be the roots of equation 1, which I denote for this. This is equation 1 which I have taken, and alpha 1 to alpha n are the roots of this which need not be distinct. Now immediately when I have these to be the roots of 1, converting the polynomial into the factor form, we know that this can be written as, that implies the polynomial generally which I denote with p of x here can be written as x power n plus p1 x power n minus 1 n minus 2, so on and so forth till pn minus 1 x plus pn can be written in this form as x minus alpha 1, x minus alpha 2, x minus alpha 3, so on and so forth till x minus is how I can write this in the roots form. So using the factors form, when I convert this, I get this. Now the question comes on further simplification of this and comparing the roots with the coefficients. The only intention of comparing the relation between roots and coefficients is that I expand this and I bring it in this form to see how they are related. So initially, to start with, x, I each time multiply x times x times x times x times x times. So how many x's are available here? We all know there are n number of x's. So x times x times x till n times is x power n is the first term which I get out here. So my first term is x power n. Then immediately to start with the next term, I have to see for next term multiplied with each of them. So first term multiplied with each of this is obtained for x power n, which is the first term. So let's see how x power n minus 1 term is obtained. Now to obtain the x power n minus 1 term, I need to have one short of x power n. That is, I remove this x and I multiply minus alpha 1 times of x till x, but one x is short. That is, I have minus alpha 1 times of x power n minus 1 is how I get this to be. Now similarly, when I use the concept of alpha 2 fixed, this x is fixed here, and when this alpha 2 minus alpha 2 is fixed, then each of x multiplied except this x gives me alpha 2 times x power n minus 1, because one short of x out of the whole of x power n gives me x power n minus 1. Now this applies to each of alpha 1, alpha 2, alpha 3, alpha n minus 1, alpha n. So I get this to be minus alpha n of x power n minus 1, such that this whole I can take x power n minus 1 common. But let's see how x power n minus 2 is obtained. Now, in order to obtain x power n minus 2, I need to have two x's removed from x power n. So I remove these two and see what exactly happens. So when I just multiply alpha 1, alpha 2, these two are going to be multiplied to the rest of the factors. So minus alpha 1 into minus alpha 2 is plus alpha 1, alpha 2 of x power n minus 2, because two of the x's are already removed. Now similarly, when I take alpha 2 and alpha 3, minus alpha 2 into minus alpha 2, these two x terms are removed, and then the whole of x power n removed with two x terms gives me alpha 2 of alpha 3 of x power n minus 2, so on and so forth. And next I get alpha 3, alpha 4, alpha 4, alpha 5. So the roots are in pairs and they are multiplied in pairs of 2. So therefore I get this to be finally, with the last being alpha n minus 1 into alpha n of x power n minus 2 is how I get this. So that way, similarly, I get each of the factors coming with x power n minus 2. Next, when I want to have x power n minus 3, I take three terms, alpha 1, alpha 2, alpha 3, where minus into minus plus, plus into minus, minus. So I get alternate plus, minus, etc., through which I construct for n minus 3, n minus 4, n minus 5 based on the number of x terms I delete from x power n. So finally, we are going to search for the constant term or the last term, that is Pn, compared with the factor form. So as I know that when I multiply each of the factors which are the constants, then I get alpha 1, alpha 2, alpha 3, alpha n minus 1 and alpha n, and there are minus signs which are n in number. So minus, minus, minus taken n times will be minus 1 whole power n, because we don't know whether n is even or odd. I take minus 1 whole power n. The sign was decided by the even n or odd n. So in this case, this would be alpha 1, alpha 2, alpha 3 times of alpha n is how I get this when I simplify for each of the factors. Now let's take everything common and then compare to see what would be the outcome. Now, continued from what we have obtained, let me rearrange, taking all x power n in the starting and taking all x power n minus 1 terms together. Then I get this to be alpha 1 plus alpha 2 plus alpha 3 till alpha n of x power n minus 1. Then taking all the combined alpha 1, alpha 2 plus alpha 2, alpha 3 plus alpha 3, alpha 4 to alpha n minus 1 alpha n of x power n minus 2, and then proceeding I get next minus term, and finally my last term is minus 1 whole power n times alpha 1, alpha 2, alpha 3 till alpha n is what I obtain when I take this in the root form. Now here comes comparing the like coefficients. Let's see what happens. Now comparing the like coefficients, I find x power n and x power n are always with the leading coefficient 1, which are equal, as can be clearly seen. Now let's see what happens with the relation between P1 and this, where I clearly see that my second coefficient P1 is minus times alpha 1 plus alpha 2 plus alpha 3 till alpha n. Next, my P2 is nothing but alpha 1, alpha 2, alpha 2, alpha 3 till alpha n minus 1 alpha n is what I get for this. And similarly, my P3 would be alpha 1, alpha 2, alpha 3, etc. and etc. So my P3 would be minus of alpha 1, alpha 2, alpha 3, 4, and 3, 4, 5, 4, 5, 6. In consecutive numbers, I get alpha n minus 2, n minus 1, and alpha n, which I get for P3 is what I get, and so on and so forth. I find that my Pn is the last term, which is nothing but minus 1 whole power n, alpha 1, alpha 2, alpha 3 till. So this is how we get alpha 1, alpha 2, alpha 3, so on and so forth till alpha n, with multiplied with minus 1 whole power n. Now each of these will relate the roots with the coefficients. The coefficients being P1, P2, P3, Pn, so on and so forth, and our roots being alpha 1, alpha 2, alpha 3, and alpha n. As I see here with the first case, it is clearly the sum of roots, which is alpha 1, alpha 2 till alpha n, which gives me the relation. So as I compare P1, P2, P3, and Pn, I see that my sum of roots, as in this case, I see that my sum of roots, whatever are the roots of the given polynomial, is always negative of the coefficient of x power n minus 1. So my sum of roots is minus P1, and my product of roots taken 2 at a time is nothing but, when I take here, I have my product of roots taken 2 at a time is P2, which is nothing but the coefficient of x power n minus 2 in case of the polynomial. So deriving, let's see what we get when we take it as a formula. So each of them, we try to take it in the form of roots and the coefficients and see how we can derive a formula out of this conclusion. So therefore, we understand that the sum of roots is minus P1, that is minus of coefficient of x power n minus 1 is how we understand the formula. Then we have sum of product of roots taken 2 at a time is given by P2, which we have taken, that is, when I take sum of product of roots taken 2 at a time, I get this to be P2, which is nothing but coefficient of x power n minus 2 of the polynomial p of x, which is considered. Now next comes sum of product of roots taken 3 at a time will be nothing but minus P3, because every time it is minus plus minus plus, so I get minus P3, which is nothing but negative of coefficient of x power n minus 3. So taken 4 at a time would be obviously P4, and how, etc., so on and so forth. Then finally the product of roots, which is denoted by minus 1 whole power n of Pn, is what I get for the product of roots, which is minus 1 whole power n Pn, and this is nothing but minus 1 whole power n of the constant term of the given equation. So whenever I have a constant term, I just multiply minus 1 whole power n, then I get all the product of roots which are equal, is how I understand each of the roots connected with the coefficients in their own respective properties.